Hello and welcome to Quarantech Tuesday. As we wait for everyone to jump on here, I'll give a brief introduction. I'm Abby Weber and I'll be your host today. I work on the marketing team here at FCT Solder, and for today's webinar, we are excited to be featuring Tony Lentz, FCT Solder Field Application Engineer, to discuss solder alloy reliability. If you've joined us for Quarantech Tuesday before, you know the drill, but for anyone here for the first time today, the webinar will be recorded and will be available to all registrants and attendees through a link that you will get in your email tomorrow. We would love to hear from you during today's presentation, and there will be time for a Q&A session towards the end. You'll see a Q&A tab at the bottom of your screen, so feel free to throw any questions you have in there. If we don't get to your question during today's webinar, we'll be sure to follow up, or you are always welcome to contact us directly. Now let's jump right in. Tony, you have the floor.
Thank you, Abby. I appreciate that. This presentation is about solder alloy reliability, and this was generously donated by Keith Sweatman. Most of this information was prepared by him and his partners within Nihon Superior, so we really appreciate his support with this work. First, we'll go over a brief introduction, talk a little bit about what is reliability, and how do solder joints play a role in the reliability of a printed circuit board assembly. We'll go over some applications for high reliability solders just briefly in order to set the stage of where they can be used. And then I'll talk in detail about the different lead-free high reliability solder alloys that are available on the market. We'll cover the composition and give a little information on the green structure and intermetallic compounds that form, which are key to how they function in order to improve reliability. And then we'll go into some detail on reliability testing. How is it done? What are we trying to measure? And then I'll have a comparison of reliability data for SN100CV and other solder alloys available on the market. And then I'll talk a little bit about a new alloy that's under development called LFC2, with some brief information about the composition, grain structure, and reliability data for that alloy. And finally, at the end, we'll have a brief summary. And of course, like Abby mentioned, we will have time for question and answer at the end of this presentation. What is reliability? So I looked up this word in the dictionary just to clarify my understanding of it. Reliability is the quality of being trustworthy or of performing consistently well, which is exactly what we're looking for with solder alloys. We want a solder alloy, which is the interconnect material used in electronic solder joints, to last for the life of the electronic assembly. That's the expectation. Not only does the solder need to provide electrical continuity, it has to provide mechanical strength and not crack or fail during the life of that device. So how do solder joints play a role in the overall reliability of a PCBA? Well, as we know that circuit boards are becoming smaller and more densely packed with components to increase the functionality within a smaller area on the circuit board surface. And that means we're adding more solder joints to the circuit board surface, which every solder joint is an opportunity for failure. So we're adding more opportunities for failure within every electronic assembly. And failure could result in something like this, where you've got a cracked solder joint creating an electrical open, and so that circuit no longer has continuity and that component's not functioning properly. Solder joint failures can occur through three major mechanisms. The first one is through the bulk of the solder joint, which is pictured here on the left. The second major failure would be an interfacial failure, or solder joint failure through the intermetallic layer between the solder bulk and the board pad, or the solder bulk and the component interface. Or third, you can get what's called pad cratering, where the pad actually rips off of the circuit board during thermal cycle or mechanical shock and vibration testing. And that indicates that the solder joint was quite strong, but the circuit board material was the weak spot in that particular assembly. What are some applications for high reliability solders? Of course, automotive provides a huge opportunity for high reliability solders, especially under the hood. So the modules that are using solder alloys are electronic control units, braking electronics, steering, and the exterior lighting controls. And the typical direction in the industry for solder alloys is using alloys that can hold up to high operating temperatures and that are also creep resistant. The electronics that are inside of the cabin are also require certain solder alloy properties. The types of electronics inside of the cabin, as we all know, are the instrumentation, power distribution, seat and interior lighting electronics, and then of course the audio infotainment system. It seems like every car has a computer screen right in the middle of the dash these days. And of course, there's a lot of electronics behind that to make that function properly. So the solder alloy direction for in-cab electronics would be lower cost, high yield alloys, and in some cases, low temperature alloys for the non-safety critical applications. What about harsh environments? Solder alloys that can hold up to the space or aircraft applications need to be high reliability. Those are areas where failure is not tolerated. Those are class 3 electronics that have to work 100% of the time. And so the solder alloys have to be able to hold up to those conditions and the stresses that are applied to them. Also, the telecom industry would be considered an application for high reliability. Telecom electronics, especially that are mounted outdoors, are being subjected to whatever the environment is that they're placed in. Now, here's some information on high reliability solder alloys that are in the market. This is a table full of high reliability solder alloys that were submitted to an INEMI solder project. I've highlighted 3 of these alloys that I'm going to be talking about in detail throughout this presentation. The first one on the table is SN100CV, which does not contain silver, but it contains bismuth, copper, and nickel. And that's the only alloy on this list that does not contain silver. Then there's SAC305, which is our baseline lead-free alloy that's most commonly used. And of course, we know that has 3% silver. And then if you look down a little farther, there's Inalot that's highlighted, which is a very popular automotive alloy. And that has several different elements in it, including 3.8% silver, 3% bismuth, 0.7 copper, 0.15 nickel, and 1.4 antimony. So it's quite the mixture of alloys, but it does seem to function very well especially in under the hood type automotive applications. Now, the interesting thing about providing an alloy without silver like SN100CV is the cost of silver has been rising dramatically over the last several months. And so the costs of any of the silver containing alloys, of course, might become prohibitive for certain users, whereas silver-free alloys might be an interesting option for them. So high reliability solders like Inalot have a cross section that looks like this. There's a tin matrix with antimony and bismuth in solid solution. Then there are Ag3SN intermetallic particles which precipitate out, as well as the copper nickel 6 tin 5 particles which precipitate out. But with alloys that contain high levels of bismuth, some of the bismuth does not stay dissolved in the tin matrix. It precipitates out as pure bismuth, like these little islands that are shown on the left. And then in some cases, those bismuth islands might precipitate out on the Ag3SN particles and agglomerate around them. So these intermetallic compound particles tend to coarsen and they lose effectiveness as strengtheners over time. They also tend to consolidate at the interface with the substrates, providing possible pathways for crack propagation because some intermetallic compounds can be more brittle than the bulk of the solder joint. High strength alloys are good for certain applications, but it doesn't always correlate to high reliability. In some cases, you need a solder alloy that will comply or creep a little or stretch a little along with the thermal cycling that's taking place in the operation of that device. Every solder manufacturer is creating the optimal formulation to find the best combination of strength, compliance, and stability for high reliability solder alloys. And that's why there are so many different options on the market. So how do we do reliability testing? Some of the options for reliability testing are electrical in nature. For example, surface insulation resistance and electrochemical migration are common tests that are used mainly to test flux materials or solder masks, conformal coatings, those sorts of things to make sure that they are electrically non-conductive, and they don't grow dendrites, or there's no corrosion caused during the course of those tests. Typically, though, daisy chain testing is used in combination with thermal testing, which is an electrical test, where the electronics will be monitoring for resistance increase over time or electrical opens, which indicate that solder joints may have cracked. Then, of course, environmental and thermal testing is the most popular type of testing that we do to measure reliability. Temperature cycling is well used, and the ranges can vary from 0 to 100 C up to -40 to 180 C, which I heard an automotive component supplier talking about recently. That's going to be a new testing protocol for them, which is quite an aggressive and extreme temperature range. Isothermal aging can also be done, usually at elevated temperatures like 125 C. And in some cases, we might combine high temperature and high humidity in order to stress those electronics in a different way. And then finally, of course, we can perform physical or chemical testing on the PCBAs. Solder joint shear and pull strength is commonly done to measure the strength of the solder joints or the assemblies. Shock and vibration testing is also used in some cases, which could be Hall pass testing, drop shock testing, and the like. And then if you require chemical testing, for example, if circuit boards are going to be mounted in, say, electronics that are used in ocean environments, you might want to subject them to salt spray testing in order to see what happens with salt corrosion on the electronic. Mixed flowing gas testing is quite an aggressive test. It helps to find creep corrosion and things like that with different metal finishes that are used on the circuit boards and the components in the solder joints. And then we might combine some of these different methods together. For example, daisy chain electrical monitoring might be done in combination with thermal cycle testing and shock and vibration in some cases. The whole goal of all these tests is to try to accelerate the failure of the circuit boards to find the characteristic life, and then also to determine what the failure mechanisms are, or where are the weak spots in the electronic assembly. Typically, reliability data is presented in a plot like this. This is called a Weibull analysis of failure rate. So the log of the failure rate is shown on the y-axis typically, and then on the x-axis we have the characteristic life, or the number of thermal cycles that the assembly reached. And then we would look at the 63% failure rate, and then that could be used as a characteristic life for the number of cycles that assembly lasted in that test method. This is pretty well recognized in our industry and is fairly common. What we're looking at here, in addition to that, is solder joint strength. We might look at electrical connection, resistance increases or opens. And then we also want to find out when the failures occur. Where do they occur during the characteristic life? So what about the different solder elements that are used in the high reliability alloys? They all have different effects. Silver has an effect in thermal cycle testing. So this is a chart of characteristic life on the y-axis, and then different thermal cycle methods on the x-axis, with increasing severity from left to right. So on the left, we have 0 to 100 C, and on the right, that goes up to -40 to 125 C. This first plot is for tin lead alloy as a baseline, and that holds its characteristic life throughout all these different thermal cycles. And then we have SN100C, which starts off with a relatively high characteristic life with the easiest thermal cycle, and then that decreases with increasing severity of thermal cycling. The same thing is true with SAC 0307 and SAC 105, SAC 205, and SAC 305, as well as SAC 405. So what we can see here is as we increase the silver content of the solder from SAC 0307 to 105, 205, 305, and 405, so the silver is essentially going from 0 in SN100C up to 4% in the SAC 405, the characteristic life is much higher when you use a temperature range of 0 to 100 C. But if you're using a temperature range of -40 to 125 C on the very right, all of those characteristic lives for the various solder alloys are the same. They all converge. So as the temperature range increases, the effect of silver on reliability actually decreases. Here's some more data for silver effects in thermal cycling, characteristic life on the y-axis, and different solder alloys. From left to right, silver is increasing in concentration on the x-axis. And we're running two different temperature cycles here. There's a 0 to 100 for 10-minute dwells and 0 to 100 for 60-minute dwells. So the first set of data with the blue bars is the 0 to 100 with 10-minute dwell times. You can see an increase in characteristic life as you go up in silver concentration in the solder alloy. If you go to 60-minute dwells, that increase in characteristic life is much less. These data points are much closer together in the red bars. So that shows that as the dwell time increases, the effect of silver on reliability decreases. So the point of these two slides that I just showed is that the thermal cycle that you pick and the dwell time that you pick has an impact on the reliability measurement for the solder alloy. And so it's important to be sure that you establish the testing criteria that is required before you go looking for the solder alloy that's going to hold up to that. Here's some cross-sectional pictures of SAC 105 and SAC 305. You can see primary tin dendrites, as well as a mixture of Ag3SN and Cu6SN5 eutectic particles within the solder matrix. And those particles are of a size and spacing that make them an obstacle to dislocation movement. And what that means is that those particles help to strengthen the solder, and they help to resist shear or cracking of the solder joints. And that shrinking effect comes from that fine dispersion of the pseudo-eutectic Ag3SN particles. Here's cross sections of SAC 105, SAC 305, and SAC 405 as soldered. And then those samples were aged to 2,500 hours at 125 C. So we did isothermal aging. So that's about 3.5 months at that temperature. The SAC 105 particles coarsened, so they agglomerated together and grew larger in size, and there's much fewer of them. The same thing happened in SAC 305 and SAC 405. So as the solder ages, the Ag3SN particles coarsen through Ostwald ripening. They also lose their effectiveness as they coarsen. So to get a more stable strengthening effect, we need to look at elements besides silver for the strengthening effect. So tin and bismuth have pretty similar empirical radii. They are 145 picometers versus 160 picometers, which means that bismuth could potentially dissolve into tin and integrate into the tin matrix pretty readily. Here's a phase diagram for tin and bismuth. In the blue highlighted region, bismuth is fully dissolved into the tin and evenly distributed throughout it. That's the region of solid solubility. And in the gray shaded region, bismuth might precipitate out and could appear as pure bismuth islands in the microstructure. Here's the new hardness of tin bismuth mixtures. Bismuth increases from left to right on the x-axis. You can see that as bismuth increases, the new hardness increases pretty dramatically, but then it plateaus between about, say, 3.5% and 9%. Bismuth definitely increases the hardness of tin, which could be considered a good strengthening effect. Here's a cross section that shows some of the bismuth phase that has precipitated out, and it tends to precipitate out along the interdendritic boundaries. And then we also have the Cu6SN5 phases shown in the same cross section. So that happens if the bismuth level is too high. So the ideal high reliability solder would have bismuth fully dissolved in solution for solid solution strengthening as a more stable mechanism. This is another cross section that shows that bismuth tends to precipitate along the crystal planes. So the bismuth might fully dissolve at the operating temperature when the solder is molten, but then as it cools down, they will reprecipitate as bismuth islands. So let's switch gears and get into some actual reliability data for these various solder alloys. So here's some tensile strength that was measured for Sac-305 versus tin, copper, nickel, bismuth, otherwise known as 100 CV. The aging that was done here is 500 hours at 150 C. The blue bars are as cast and the red bars are the aged numbers. So you can see the tensile strength drops for Sac-305 with aging, whereas with SN100 CV, it remains very stable. And that's the difference between particle strengthening, which is what Sac-305 uses, and the effectiveness fades as the particles coarsen through aging. Whereas solid solution strengthening, which is what's used in SN100 CV, is very stable because the bismuth stays dissolved into the tin matrix. Here's strain versus time in a creep test. And this creep test was done at 125 C with 120 kilogram load. The red curve is Sac-305 and the green curve is SN100 CV. The creep accelerates with the Sac-305 as the Ag3SN particles coarsen, which happens between hours 3 and 4. Here's shear strength as soldered for SN100 CV versus Sac-305. Sac-305 are the red bars for different component types. And you can see as the component types, they increase in size from left to right. As the components increase in size, shear strength goes up, which is expected. But the tin, copper, nickel, bismuth solder has higher shear strength overall than Sac-305 in this test, but they both increase with increasing component size. And then after thermal cycling was done, 2000 hours, -40 to +25 C, you can see the overall shear force drops off for both solder types, but the SN100 CV still outperforms the Sac-305 shear force. Here's a chart showing isothermal shear fatigue for a copper substrate as soldered. On this particular Weibull plot, you've got the blue dots are SN100C for comparison, and then the green dots are SN100 CV, and then the red dots are Sac-305. So upon initial testing as soldered, Sac-305 has a longer life than the other two solder alloys. And then after aging 1680 hours at 125 C, you can see that these curves have moved around. The red squares for Sac-305 now have a shorter life than the tin, copper, nickel, bismuth, which is the green diamonds. And so that just shows again that Sac-305 loses its effectiveness, its strength over time. And here's another data chart showing after aging of 4200 hours at 125 C. Once again, these curves have moved around, and SN100 C and Sac-305 are starting to intersect in terms of their characteristic life or the number of cycles that they lasted. Whereas the tin, copper, nickel, bismuth has the longest life or lasted for the highest number of cycles. So here's isothermal fatigue data on a copper substrate. Characteristic life is on the y-axis and aging time on the x-axis. That's the curve for SN100C alloy, which is fairly stable over the life of this test. There's SN100CV, which has a higher characteristic life than SN100C. And it is also stable over the life of this test out to 4200 hours. And there's the Sac-305 curve in green. So Sac-305 initially has a much higher characteristic life, but then it drops off dramatically by 1000 hours of aging time. And then it holds at that level, which is much lower than the SN100CV life. So the initial advantage of as soldered Sac-305 is quickly lost due to that coarsening of the Ag3SN particles, whereas SN100CV maintains a clear long-term advantage over Sac-305. Here's isothermal fatigue data on an ENIG substrate. The last chart was on a copper substrate. So there's the SN100C data, which is again very low characteristic life, but it's stable over the duration of the test, which is 2500 hours. SN100CV on an ENIG substrate drops off and then stabilizes above the SN100C life. And then Sac-305 is pretty similar to the SN100C. It's a little higher initially, but then it drops off to match the characteristic life of the SN100C. So on an ENIG substrate, SN100CV still maintains an advantage over Sac-305. It's the bismuth in S100CV that actually suppresses the IMC formation and helps to lengthen that life or make it a little more stable. What about thermal cycling and reliability? Here's a chart of different solder alloys that were tested in a paper written by Francis Matuku in March 2017. You've got tin lead and SAC 105 as controls at the top of the chart, and then S100CV and violet, which is a low process temperature alloy included in a NASA project. And then you've got SAC 305, Inalot, and Indalloy 271. So the first column with the blue arrow that's labeled precipitate strengthening shows the concentration of the elements that participate in precipitation, which means they solidify out of the matrix as individual particles or intermetallic particles like Ag3SN. And then on the right, the right-hand column that says solid solution strengthening is the concentration of the elements that stay dissolved within the tin matrix and provide a more stable effect over a period of time. And so, for example, SAC 105 only has 1.5% of precipitate strengthening elements and no solid solution strengthening elements. So it's going to lose strength over time. SN100CV, however, has a fairly low concentration of precipitate elements, 0.7 copper, and 1.5% bismuth is the solid solution strengthening element within that alloy. Violet has mainly solid solution strengtheners as well, 2.75 versus 6%. And then if you jump down to Inalot, you see Inalot almost has an equal amount of precipitate strengthening at 4.2% versus solid solution strengthening elements at 4.1%. And Indalloy 271 has a very high concentration of both, but a higher concentration of solid solution strengthening elements. So here's the test vehicle that was used in that project. It has a variety of different types of components. The three components that I'm going to be talking about are the PBLGA 676s, the CVLGA 97s, and the MLF 100. So here's data for the MLF 100 with a temperature cycle of -40 to 125 C on an OSP finish. The different colored curves are, of course, all the solder alloys that were tested, and cycles to failure is on the x-axis. So the alloy that lasted the longest is the golden triangles on the right, which is Inalot. And then the blue dots and the blue triangles are tin lead alloy and Indalloy 271, which are fairly close. And then the red squares are SN100CV, which is solidly in the middle of the pack. And just for comparison, SAC 305 are the gray triangles, which are all the way on the left-hand side of this chart. So they had one of the lowest lives. So SAC 305 did not survive this test very well with that particular component. Here's the MLF 100 data on ENIG. The trends are pretty similar here. You've got Inalot performing with the longest life, followed by tin lead and Indalloy 271. And then S100CV is the red squares, again, pretty solidly in the middle. And then you've got SAC 305, the gray triangles, and SAC 105, the green diamonds on the left. So those are the worst performing elements or worst performing solder alloys in this particular chart. Here's a chart for an LGA 97 with the same temperature cycle. Characteristic life is on the y-axis, and the different solder alloys are across the x-axis. The blue bar is on the OSP surface finish, and the red bars are on the ENIG surface finish. And you can see the same trends are formed here for both surface finishes. You've got tin lead having the lowest overall characteristic life for that component. And then as you go from left to right, SAC 105, SAC 305, SN100CV is solidly in the middle of that data, followed by Violet, Inalot, and Indalloy 271, which performed the best for that particular component. And then here's the data for the LGA 208 with three of the alloys, SAC 305, Inalot, and SN100CV. So the OSP data shows SAC 305 has the lowest life, Inalot was in the middle, and SN100CV actually was the best performing alloy on OSP. And on ENIG, SAC 305 again had the lowest life, and Inalot and SN100CV were tied for the lifespan that they lasted for this LGA 208 component. Here's that same data for a BGA 208 component. Again, you've got Inalot. Inalot here, in this case, performed the worst. Inalot had the lowest characteristic life, followed by SAC305 and SO100CV, which are about the same for OSP. And then on ENIG, again, Inalot was the lowest performing alloy. SAC305 is in the middle and just a little bit lower than SO100CV on ENIG. Here's some data on aging and reliability. So this is an LGA 256 that was thermal cycled from 0 to 100C as soldered. And you can see you've got the green triangles, or green diamonds, excuse me, are Indoloy 271, and that had the longest life, followed by SO100CV, which is in the middle, and SAC305, which is to the left. Those are the red squares. Here's that same data set, but after aging 6 weeks at 125C. SAC305 is again the lowest life alloy in this test. And then you've got SO100CV and Indoloy matching each other. So their lives overlapped after aging. Here's aging data for BGA 360 on an ENIG surface finish. The blue bars are as soldered. So SO100CV outperforms SAC305. And then after aging 6 weeks at 125C, again, both of the lifespans dropped a bit after aging, but SAC305 still had a lower life than SO100CV. So here's an overall ranking that was summarized in this work. What you have in the first column are the different components that were used, and then the different surface finishes, copper OSP and ENIG. And then in the very center, like the green highlighted column is SAC305 for reference. So the scoring key on this is anything with a 1 or a 2, or the green highlighted cells are the longest life or the best performing combinations. And then the red colored cells are the worst performing combinations with scores of 6 or 7 in them. So if you look at the SAC305 column close to the right-hand side of this table, to the right of that are SAC105 and tin lead, which performed worse than SAC305. And then to the left of that, we saw a lifetime increase for SN100CV, Violet, Inalot, and Indoloy 271. So Indoloy 271 overall performed the best, but SN100CV was clearly outperforming SAC305 alloy in this summary. But what about the failure modes that we saw for those different alloys? So like I mentioned earlier, we have 3 different failure modes: through the bulk, interfacial failure modes, and pad cratering failure modes. So through the bulk is a desirable failure mode. It's actually a defect that's repairable. You could resolder that component if necessary. Of course, if that circuit board's out in the field, any failure is not necessarily ideal. It's not desired. But through the bulk means that you didn't rip apart your circuit board or your component, and it's not due to intermetallic growth and embrittlement over time. So interfacial failures are usually due to a brittle IMC layer, which thickens over time. And that's undesirable because that's uncontrollable. You don't know when that's going to happen. Pad cratering also might indicate that your solder alloy was too strong and too stiff and didn't comply or move with thermal cycling, and the materials around it were the weak spot. And so if the pad rips out of the circuit board, of course, that's not a repairable defect. So here's 3 of the different components that were tested: the different surface finishes, copper OSP on the left and ENIG on the right in the blue highlighted areas, and then the different alloys that were tested in this work. So these green circled cells are the tin copper nickel bismuth alloy, or SO100CV. In all cases for these components, failures were through the bulk of the solder, which was desirable. The automotive alloy that was tested and Inalot had failures that were interfacial or pad cratering type failures, which is undesirable. And then some of the other alloys that were tested, like Violet, had interfacial and IMC failures. So Violet tends to fail at the interfacial or IMC interface. Inalot and the other automotive alloy that was tested tended to fail with a mixture of failures, had some interfacial failures, some IMC failures, some pad cratering failures. SN100CV mostly had a failure in the bulk solder. So let's switch gears and talk about a new high reliability alloy that's being offered. Here's a performance measurement on the y-axis versus number of thermal cycles on the x-axis for a resistor component. The thermal cycle was -40 to 125C. LFC2 is this new alloy, which is the blue data. Then we've got S100CV for comparison, which is the green data, and then SAC305 again is the baseline. You can see that LFC2 was much more stable in terms of shear performance throughout this thermal cycle test. And SAC305 showed much faster deterioration than either one of those other two alloys. Here's cross-sectional pictures of some of that testing. You can see the LFC2 cross-section shows very little cracking. There's a little bit of cracking going on underneath the body of that component, but otherwise up the sidewall, it looks pretty clean. SAC305 has much more cracking propagating from both underneath the component and from the top down through that solder joint. And then S100CV is in between these other two, where there's some cracking propagating from both surfaces, but not as dramatic as the SAC305. Here are the properties of LFC2 as compared to SAC305 and S100CV, just for reference. I'm not going to read through this table because I don't want to bore you with all of the numbers and data here. Just for a quick highlight though, the melting points of these alloys for comparison. In this particular test, SAC305 was measured to have a melting range of 218 to 219. Typically it's written as 217 to 220C in most literature. SN100CV has a melting range of 221 to 225, but it is reflowable in a profile that's identical to SAC305. And then LFC2 has a slightly lower melting range, which is 205 to 213C, and that would enable the use of a slightly cooler reflow profile. So in summary, there are many high reliability solder alloys that are available. There's different elements that are used to enhance the strength and the life of these tin-based solders, including silver, bismuth, indium, copper, nickel, and antimony. And sometimes combinations of all of them are used. Solid solution strengthening that's used in SN100CV gives a more stable effect than particle strengthening in SAC type alloys, which degrades over time. But with all of these different solder alloys, we can achieve the creation of high reliability electronic assemblies. You just have to make sure you pick the correct alloy for the application and you understand what type of conditions it's going to be subjected to make an educated decision on the correct solder alloy. Thank you very much for your time and your attention for listening to this presentation. Now we have time for questions.
Thanks, Tony. Like you said, the floor is open for questions, and I think I saw at least one come through here. Jordy is wondering, do you have any data on added gold percentage?
We do not. We don't have data on that at this time.
How does solder paste flux affect reliability of electronics?
Well, solder paste flux, which wasn't really the topic of this conversation, but solder paste flux certainly has an effect on reliability, especially no clean solder paste fluxes, which are left on the assembly. And depending on the conditions in which they're used and how they're handled, no clean fluxes can sometimes cause failures over the life of a circuit board, because there can be unreacted activators or potentially halogens left behind in a flux residue. And if that flux residue is disturbed, those things could create corrosion or electrochemical migration or dendritic growth over the life of the assembly.
Great, thank you. Are some solder alloys recommended for or designed for specific applications?
Yes, certainly. Just like I was showing here, there's a lot of data and many different test methods that are used to determine the reliability of solder alloys. But the reliability really depends largely on the end use or the application of that electronic device. And so it's highly important to understand, okay, what's the expected lifespan? Does this thing have to last 2 years, like a cell phone, for example? Or does it have to last 100 years if it's something we're, putting in the upper atmosphere in space, for example, in orbit? So you have to understand the lifespan and then also the conditions under which it's going to be used. Like in an engine of a car, of course, you've got thermal shock going on. That solder alloy could be at negative 20 degrees C outside in the winter, and then you turn the engine on and all of a sudden it's 140 C in the engine compartment. Plus there's vibration going on. So those electronic assemblies have to be built correctly in order to withstand that environment. And the choice of the solder alloy is, of course, an important decision there because it is the interconnect material for those solder joints.
Great, thank you, Tony. Mike is asking, is negative 55 C realistic for the cold cycle? Is 150 C realistic for the hot cycle?
I think those temperatures are fairly extreme. Obviously, outdoors in an outdoor environment, we would never see those types of temperatures. But inside of an electronic device, if it's sealed up with other heat happening there, it could definitely reach 150 C. It really, again, depends on the application of the device and the environment it's going into. And do those components generate heat? Is there adequate thermal wicking to relieve the heat? Is there adequate ventilation? Those are all the questions to consider when you're looking at a temperature range for thermal cycle testing. I hope that answers your question, Mike.
Thanks, Tony. What are the differences in solid solution strengthening versus particle strengthening? If you could explain some more.
So solid solution strengthening is like it sounds. So if you imagine, say, dissolving salt in water, salt completely dissolves and the water looks clear and it's totally part of the solution. So it's a uniform solution. Whereas if you mix, say, metal particles into a glass of water, the metal particles are not going to dissolve in the water. It's going to remain precipitated out. The same thing can happen in tin. Imagine tin is the water in this case. Tin is dissolving the other elements like silver and bismuth and copper. There's only a certain amount of bismuth that can dissolve into the tin, up to about somewhere around 1.5%. And that amount of bismuth will stay dissolved at room temperature. Whereas if you add, say, 4% bismuth to the solder, that extra amount that won't stay dissolved will precipitate out as individual bismuth particles. And that's where they become particle strengtheners. Or when you add silver to any kind of a tin copper mixture, you get Ag3SN particles. And those are not soluble in the tin, so they precipitate out as fine particles, like I showed in the cross-sectional pictures. And so the solid solution strengthening, because the elements are fully dissolved in the tin matrix, they stay dissolved over the life of that test and they don't change. And so they maintain their strengthening effect throughout thermal aging and thermal cycle testing. Whereas particles that are precipitated out tend to agglomerate and collect together and become larger, and they lose their effectiveness. They no longer provide the strength that they once did when it was small, finely dispersed particles.
Thank you, Tony. Are there any other joining materials that can be used in electronic devices besides solder?
Yes, there are. Actually, there are sintering materials which are becoming more popular, not necessarily for component soldering to PCBAs, but for interconnect electronics. Sintered materials don't have to be heated past the melting point, which is good because they're using metals like copper or pure silver, which have very high melting points. And so they're able to put those materials onto the interconnect, heat them enough to where they sinter or bind together, and then they form an electrical connection and a pretty strong mechanical connection for that solder joint. There's also conductive inks, which are sometimes used in the bare board manufacturing process. For example, if you want to have vias in your pads, in some cases, you might want to fill those vias with a conductive ink to make a completely conductive solid cylinder of metal underneath the pad. And those are typically screen printed and then reflowed to harden up. And then those can be cap plated or covered with copper, and so that you have a flat pad surface on the top.
Great, thank you. Denny is asking, is there enough difference between new hardness to quickly tell a difference between eutectic solder and PB-free, between the PB-free alloys?
Initial new hardness, I'm not sure. I'd have to go back and look at that data. That's certainly something I could get back to you on.
Sounds good, thank you. Well, we are coming up on our time here today, so we'll start wrapping things up. Thank you again, Tony, for joining us today.
Certainly, it's my pleasure. Thank you all for attending.
Yeah, thank you everyone for your attendance and participation. And just as a reminder, this webinar was recorded and you can access it through a link you'll receive in your email. As we mentioned before, don't hesitate to reach out to us with any questions and be on the lookout for future topics. We hope to see you in June for the next Quarantech Tuesday, and have a great rest of your day.